We were not all raised in water, but we were certainly born there, regardless of size and shape. Under the surface of oceans and lakes, inside the eggs of birds, and in the uterus of mammals, we arrive to life in water. But also in the microscopic wetlands of our bodies, where new cells, but also viruses and bacteria are born, raised and multiplied in infinite numbers in water. Without this exceptional molecule, none of us would even exist. It has absolutely unique and life-supporting properties that have baffled scientists for decades. The battle for answers to the origin of these intriguing qualities have caused severe controversy in the science world. This film follows the scientific quest and reveals surprising new discoveries.
All liquids on this planet, all of them behave in a similar manner. And then water completely misbehaves. It's like a child that you cannot control.
I was thinking, water, isn't this very simple, ordinary? Then actually my PhD advisor came back from a conference and he gave me one of Anders' papers. And that was kind of the beginning, let's say, of the rabbit hole. I just followed the rabbit hole by an accident.
Water is so fascinating because we are in touch with it every day. We can drink it, we can swim in it, we can go skiing. That's my favorite hobby. And we do this every day, but still we don't understand how water is acting on a molecular level.
Once upon a time, I decided, why don't I go to a conference, which is close to my heart, but I've never been working on it. And it was a conference on water and ice in Newfoundland. And then I stumbled into a lot of anomalies, which then made me more and more interested in what's going on with water. So today, we all know, that the future of our planet depends how we are dealing with water. It's a very, very important material. It's the material of our life.
What we see in front of us here is something remarkable of water. The force the ocean can have to carve out a sculpture. Beautiful, simply beautiful.
Anders Nilsson is a professor in physics at the universities of Stockholm and Stanford. Our journey into the mysteries of water begins in 2011 on an island outside the Swedish capital, where Anders revealed to us the strange and unique behavior of water.
We have forgotten our connection to water, I think, in many respects. We can replace many things on this planet with alternatives, but we can never replace water. Water is most unusual. We might even call it mysterious, since its properties really deviates a lot from what we call normal liquid. A normal liquid would be like alcohol, oil, ether, any type of liquid, which typically behave in the same way, and water sticks out. Usually, if we have a solid, it's more dense than the liquid.
If you take a glass of alcohol and then freeze the alcohol with liquid nitrogen, the frozen pieces are heavier and more dense than the liquid, and they sink.
But take a look at the glass of ice water, and you will see that the ice floats on the water. That's actually quite peculiar that the solid is actually less dense than the liquid. It's mysterious. You will see that the temperature at the bottom of the glass is 4 degrees Celsius. So water becomes heaviest at 4 degrees. It's quite weird somehow, because between 4 degrees and 0 degrees, it means that as you lower the temperature, we would then usually expect that things will contract, but water instead expands. Ice will always form on the surface of the ocean, protecting the marine life, everything below in the deep waters. And the density maximum had allowed always to be 4 degrees at the bottom, so if it will become cooler, it will rise up, and other water will come down, so it prevents actually the ocean for bottom freezing, and therefore marine life could actually evolve.
If ice had been heavier than liquid water, the cold ocean floors of the planet would be covered with endless ice and would never have enabled life on Earth. A crystal clear liquid composed of a chemical compound hosting nothing else than that.
Also, the density maximum allows a lot of circulation of water in the ocean, bringing nutrition from the surface down into the ocean. So on all levels in the ocean, all depths, life can be sustainable. Another very, very unusual property is what's called heat capacity. It gives the information how much heat we can store in the water.
In the oceans, majestic streams run for thousands of miles, carrying nourishment and fish, but primarily heat and cold between the climate zones of the globe.
It's due to the high heat capacity that we in Europe could have a very, very nice climate, because the Gulf Stream moves hot water up from the Caribbean up to Europe. And if water would have been like a normal liquid, all that water would have cooled down way before it came to Europe. So the high heat capacity is really what makes us have an enjoyable life. All the currents that flows around in the world of the water, stabilizing all these different climates. Water has a very high surface tension, much higher than nearly all other liquids. And that particular property actually makes the spiders to be able to walk on water. And we know that if we put a drop of soap in water, the poor spider will drown.
Surface tension is only a few layers of strongly bonded water molecules that can carry enormous weight in relative terms, such as a razor blade of steel. But just a small drop of soap replaces the top layer and the tension disappears.
Another property that is directly related to surface tension is what we call capillary forces. If we put a straw in our drink, we can see there is a little bit of liquid pulled up into the straw. That is the capillary force, which is actually directly related to how the plants can actually bring up water through its small pores, useful in the photosynthesis and all the biological and biochemical reactions in the plants for sustaining its life. And if we think about it, these unusual properties is also actually the basis of our existence. So with my research, I'm focused very much on the molecular structure and to really understand these very fundamental properties of water. And has the unusual properties of water any connection to the life process itself?
Our understanding of water and its properties will be vital for years to come. Our planet is obviously in great need of assistance.
We will see much more hurricanes. We will see much more heavy rains in certain regions. And the effect of the climate change will most likely be seen through water.
Water is really the guardian of life on our planet. Since the beginning of time, water wraps us all in a blanket of atmosphere, tempering the climate into a span of degrees that suits all living organisms. Creating a thermostat for the entire planet. Water molecules take on a variety of appearances, performing tricks that are hard to believe unless you look carefully, putting it to the test under extreme conditions.
Many people are interested in mysterious or often called esoteric properties of water. One particular experiment was conducted in the 19th century. It shows how electricity and charge in water can generate what's called the water bridge. Everything is moving in a certain way that...
So it consists, as you can see, of two beakers of pure water. And down here I have a power supply, as you can say, to supply very high voltage, more than 10,000 volts. So the trick is to move this one very slowly apart and then see what happens. So I'm pulling slowly here, and you can see there's kind of a rope-like structure forming now. It's almost 1 centimeter. And if you have really good eyes, you can sense that there's movement from the red to this black beaker and from the black back again. So my understanding is that it's like two spirals, two vortices running in opposite directions.
What we aim to find is an explanation how water looks in the inner molecular structure. How can we make a full picture of this tiny little molecule in different situations? If you look at snowflakes in the winter, beside the fact that they're really beautiful and everyone is unique and they are so different, but all of them have 6 arms. And you have to dig deep into the molecular structure to understand that there is a 6-fold symmetry in the crystal structure that gives these 6 arms on the snowflakes as well.
But it's not only unique, it's all symmetric. How it grows depends on the temperature and the humidity. So it can form either plates, rods, all sorts of forms. It will travel in the atmosphere and be visiting different temperature region and humidity. But each snowflake has taken a different pathway, and therefore it's different.
Another strange property that we normally don't reflect over is the fact that we can travel really fast without wheels on the surface of solid water.
You may have wondered why ice is slippery, right? And why we can actually skate on ice, because on this floor, obviously, we can't skate. And there have been a number of explanations. So the most popular is that it's due to a phenomenon called pressure melting.
That pressure on ice would make it melt is easy to disprove, since a heavy object doesn't create more slipperiness than a light one. Another suggestion is that it is friction heat from the skate that makes it glide.
And it probably is true to some extent, but it wouldn't explain why, even if you just stand on ice, it's already slippery. And so then we had to look for a new explanation, in a way, to study this phenomenon. And this was actually a joint project between my brother and me. So it's the Bond family that worked together. So he actually did a very simple experiment where he put a little steel ball on ice, and then he rotated the ball. And so that's how he measured the coefficient of friction. And what we found is that there are actually two types of water molecules at the surface. There are water molecules that have one OH group that sticks into the air, but they still have three other connections to the surface. And then there are other water molecules that only have two connections to the rest of the ice. And it's like if you're in a bar and you're sitting on a stool, when it has 3 feet, it's completely stable. When it has 2 feet, you know it's going to wobble. And in fact, we found that these wobbly water molecules that have only 2 connections to the ice, they can very easily sort of tilt and then roll over the surface. As it tumbles, the free guy becomes bound and the bound guy becomes free. And it can tumble very quickly over the surface in that way. And that's actually what makes ice slippery. These doubly bound water molecules essentially act like marbles on a floor. They can roll along with your skate or with your shoe. They simply move along with whatever is on the ice, and they actually essentially lubricate the contact.
But perhaps the strangest appearance of water is water in space. Inside planets with vast amounts of water, in a condition that doesn't resemble anything we have on Earth. The scientific calculations show that Neptune and Uranus contain water in one of the most peculiar forms. Superionic water is a kind of crystalline ice squeezed under millions of bars of pressure, which conducts electricity. Water, transformed to something black and very different under millions of bars of pressure and enormous heat. Water that starts to act like metal, conducting electricity, which has been measured by astronomers as a strong magnetic field around the planet.
Water is a kind of a mystical thing for me. It has a kind of gravitation, like it attracts the interest. It's an open puzzle, so to say, that is calling for an answer.
We all know that the water molecule is H2O. One oxygen atom bonded with 2 hydrogen atoms. However, what makes the magic in water is how the molecules are connected.
It's a very, very complex structure which gives rise, to a new type of bonding which is mediated by the hydrogen in the water.
The molecules bind to each other two positive hydrogen protons interact with the negative oxygen. The charge on the oxygen atom reaches out to the positive hydrogens, and they can form different local structures.
Let us look at hydrogen bonds making the connection between the molecules. Without those, liquid water would not exist on planet Earth. Only water vapor and no life.
If you follow the logic, water should boil at very low temperature, and then life around 20 Celsius should not exist because water would be a vapor. But because of the hydrogen bonds between the water molecule, the existence of the liquid state is typically between 0 and 100 Celsius, which is exactly where life can occur.
There are 20 anomalies or even more anomalies which deviate strongly from all the other liquids we know. And they are not deviating by 1% or 2%, so it's dramatically different.
And we're still trying to understand why that is. Why is this anomalies appearing? What is the origin of these anomalies?
That the reason for water's strange behaviour is hidden in the molecular structure has been a good guess among scientists for quite a while. But it is extremely difficult to study, since water molecules change their positions faster than a trillionth of a second. In Boston, back in the beginning of the 1990s, a group of physicists, Francesco Scortino, Gene Stanley, and Peter Poole, started to come close to water's secrets by using computer simulations. They were able to use the most advanced computer of the time for big data handling, that basically had the power of a low-budget smartphone today. They entered the known properties for water components, oxygen and hydrogen, and water's known behaviour during certain temperatures and pressure.
I've been studying water for 30 years more nowadays. And at that time I was doing numerical simulation. The richness of this numerical experiment is the fact that we have the coordinates and the velocities of 10,000 water molecules. So we really know where they are, how they move, what they do, their friends, and really check microscopic properties.
And it's during the computer simulations that the scientists suddenly make a key discovery. Inside the calculated network of water molecules, they detect signs that water can exist as two different liquids, with structures that would link water molecules to each other in very different ways.
Usually in an atomic system, a liquid, each atom is surrounded by 12 other atoms in a liquid state. In water, the water molecule is surrounded by only 4 other. Those other molecules, it's bonded with a nitrogen bond, a peculiar, very strong interaction. And today, I mean, after 30 years of studies, we have realized that these anomalies arise from the competition of 2 different local structures. It's completely new, a completely crazy idea. Right? And it was crazy 30 years ago. No one has ever tried to propose anything similar to that. So we really spent a lot of time and a lot of energies in convincing the scientific community that was a possible explanation of the water anomalies.
This means that in the computer simulations, the hydrogen bonds make it possible for water molecules to bind to each other in 2 different ways. A spacious version called low density to the left, and a tighter connection called high density to the right. 2 different liquids formed from the same molecule.
The approach could be done either this way, and this forms a very open structure, or this way, And this forms a more compact structure. The way in which these water molecules approach each other while they move and dance in the liquid, we know that this kind of fluctuation between a low density and a high density liquid do exist already at ambient temperature.
In the proposed hypothesis, the two liquids could coexist when exposed to low temperature and high pressure, as two macroscopic phases visible to the eye, just like water and ice in a glass of ice water. However, in our ordinary water, under normal pressure and temperature, we have only one phase, and there it cannot decide if it wants to be high or low density, tight or airy, fluctuating back and forth. When warm, it's mostly high density, and when cold, more low.
These two structures fluctuate like a dance, and they have all sorts of shapes. And we could think about a very simple analogy to understand why this is. So, if we could imagine a dance restaurant where we are putting out a table where people will sit and drink and eat. And as they sit in these tables, they are in a very organized form. They sit still, they don't move around. And since there is a table, they take up a little bit space. Around the table, people are dancing in a very excited state. They are dancing and moving around and having fun, and they are therefore also more packed. So we could think about it as the tables are the more low energy, people are still, we can call it low energy. And then this high density structure where everything is moving around much more faster, and people have what we call in the scientific word higher entropy. Higher entropy is a concept which is a little bit how disordered the system is, not so arranged.
When water freezes, the molecules are rearranged in a very different way, in rigid hexagonal rings.
The fact that the crystal ice, ordinary ice, is less dense than water, so it floats on water, which of course is very important for climatic reasons. You know, if it didn't, it would sink to the bottom and the fish would die in the winter. It's actually a very open structure. It's really made of hexagonal rings with an open space in the middle, so it's not a very dense structure. If you then melt that, when you melt it, you're taking away the requirement to be a crystal, to be a regular repeating arrangement of molecules. And in doing so, it gives those molecules the chance to occupy less space.
The dance of fluctuating local structures shows how density maximum in water appears. At 100 degrees centigrade, we have only high-density red molecules that move rapidly and therefore take up a lot of space. As the temperature lowers, the molecules move more slowly and thereby come closer, decreasing the volume of the water in the glass and increasing its density. At 50 degrees, we start to see the appearance of low-density blue molecules, and when the temperature decreases further, the low-density regions grow and the water level in the glass stops sinking, since the blue molecules take up more space. When the water has reached its density maximum at 4 degrees, the liquid is balanced between the tight red molecular structures and the blue area ones. Between 4 degrees and 0, the blue airy version of water takes over and the volume in the glass rises. Water can be supercooled below 0 degrees without freezing if the water is very pure. And in doing so, the blue becomes even more dominant. But there is one problem. The two-liquid water is just a hypothesis presented through computer simulations. And there are several other competing theories to explain these water anomalies. In the end, it's all about experimental testing with the actual substance, water.
From that theory, you can predict many properties, and it is possible to match the observed properties of water in experiments. So it's an attractive description of water because it can reproduce what is known, but on top of that, it predicts some very peculiar behavior, like the possibility of transition between two liquid phases of water. So this would occur at so low temperatures that it's very hard to observe them experimentally.
We have a pressure volume.
At the time of the discovery by Francesco Scortino and his colleagues in Boston, there was absolutely no way to experimentally test water on a molecular level far below the freezing point. But 25 years later, Anders has an idea: how to study water extremely fast before it freezes, to use a super exclusive tool based on X-rays, and to try it on pure water. He sets out to gather a team of top scientists and starts designing an experiment that has never been carried out before, not even considered possible.
Water has been controversial since almost a century. There has been many ideas and many different schools of thinking. And part of the challenge has been that we have lacked experimental evidence for different ideas, to test different ideas. And my own personal goal has been to really develop new experimental methods, new experimental approaches to test ideas with water research.
SLAC is a huge experimental facility at Stanford University outside San Francisco, where advanced molecular research of different kinds is performed. One of their features is a 3-kilometer-long particle accelerator installed in the longest building in the world.
I was recruited to Stanford in 2000, and I started that just when the development began with what's called the LINAC coherent light source, the first X-ray laser.
So LCLS was built about 10 years ago, tuned to produce X-rays, so we can capture the motion of atoms and molecules, look at how the cells in our body work, look at how chemicals drive all the natural processes in the world. But it delivers those X-rays in an ultra-fast burst of light, a millionth of a billionth of a second.
Magnets in the tube make the electrons wiggle, starting to produce X-ray pulses. Formed from electrons in straight lines, generating super high intensity.
It can freeze frame the motion of those atoms and molecules and watch how they interact with each other, how chemical bonds are made, how they're broken, and how the whole system evolves after that.
And following all the ideas, what it could do, it became very apparent for me that we can open a complete new door in water science by using X-ray lasers.
So, some aspects of science, we knew what to expect. But every now and again, you get a real surprise. A team comes along and decides to investigate something you just hadn't previously thought of. And it actually happened at the very beginning. A team led by Anders Nielsen came along and looked at it very differently and said, we could use this X-ray laser to look not at the biological molecules, but to look at water itself.
The hypothesis of two liquids has, of course, eluded the scientific community for decades. And I started thinking about this, how such an experiment could be done. First, we developed the droplets, so we could go into these very low temperatures at atmospheric pressure.
Anders and the Swedish team have developed a very thin stream of micro droplets, only visible on the computer screen. The ultra-pure droplets have been supercooled to -45 degrees in order to capture the state of water where the two liquids can coexist. Inside the SLAC X-ray laser, a large number of shots are fired at the microscopic droplets during a fraction of a second. But still, no sign of the two liquids. There is only one phase shown in the experiment, and their beam time at SLAC has ended. Now the team has to rethink before their next attempt.
Can you focus a little bit better?
Back in Sweden, they decide to test whether adding very high pressure to the water samples might be what's necessary. They freeze water under high pressure, but later at the X-ray laser experiment, they can warm up into the liquid phase and search for the two liquids.
So the first step in building a very complicated piece of equipment or a bit complicated setup is actually imagination. You have to sit back and think and try to visualize it in your head. That's always the first step. Then you have to visualize it in the virtual world. So that from the computer you have to transform it into lab equipment, which means after a while it's a little bit like a musician. You develop a certain feeling for it, how the setup should be in order to make it work. So the back of your head is doing a lot of the work at this point.
Ensuring water remains liquid below -45 degrees centigrade, using liquid nitrogen, while applying many thousands of atmospheres in pressure, is tough. The slightest movement turns the liquid to ice. And most of the samples are crystallized during transport or preparation.
If we compress the ice at very low temperatures, we talk about temperatures of -200 degrees centigrade, then this crystal structure collapses and suddenly forms something that we call amorphous ice. The water molecules are not longer arranged like in a crystal structure, but they are disordered.
The crushed ice structure becomes a kind of slow liquid called a glass, similar to glass as we know it.
So a glass is a liquid that's lost its ability to flow, pure and simple. Why has it lost its ability to flow? Because as the temperature goes down, the molecules move more and more slowly.
It's trapped, but at the same time it's not moving anymore. So it's really a disordered glassy state.
And it's only after a while when you take them out and it's heated up and it goes into the liquid state. From the glass into them, these motions start to be unlocked and they start to move again. Then the molecules say, oh my God, I'm no longer at these 1,000 atmosphere, I'm at 1 atmosphere, and maybe I should start to expand. And as it expands, it goes into a transition to the other form, which is low density.
And it's 20–25% difference in density. That's why it looks like a popcorn effect.
And it's precisely here, between the glassy state and the slowly moving liquid, where one can hope to see the signs of the two liquid water.
These two liquids that we're talking about, they're fighting with each other, they're competing. So in the one case, it's like you're in the land of the low density liquid. This is, everybody's there low density, except from some small crowds that pop up here and there of high density liquids, some kind of rebels that appear, and then the low density liquid tries to make it disappear. So that's like, you can almost think about it in some kind of uproar that is happening there locally. Whereas if you are in the land of the high density liquid, there you mainly have high density liquid citizens that And then there are some small red balls of low density liquid that pop up locally. Now what is very interesting is when you go on the boundaries. What happens at the boundaries? Who is the boss there? That's actually where the liquid to liquid transition is happening.
Preparation for the experiment is ready. The sample is generated in 2,000 bars of pressure and cooled to -200 centigrade. At this low temperature, the molecules are completely stuck and can be removed for transport, cooled in liquid nitrogen.
There has been so many different ideas about water. Usually in science it's almost impossible to prove anything. Usually it works by disproving. So we test ideas and we see if they are falsified or if they stand the test. But since water has been so difficult to actually get experimental information, many of these ideas has not been fully tested.
This part of the experiment will not be performed in Stanford, but at the new X-ray laser facility in Pohang, South Korea. And the team is on their way.
And Daniel, we will be like 9 people. So we can have then a team of 20 people for the experiment.
One of the team members is preparing the experiment on site in Pohang.
This is a detector for the layer mix MX225.
Yes.
And this is a large area detector. I mean, I spoke with the laser staff here, and he said he can make 100 micron.
짜리 초고성능 거대 현미경인 포항 4세대 방사광 가속기가
한국과 스웨덴 공동 연구팀이 액체 질소로 중수
Korean TV is on site for the water experiment, which is the very first in the newly built facility.
저희가 좀 집중을 해야 되는데.
At the X-ray laser in Stanford, the team did manage to take pictures of liquid water, cooled down to -45 degrees centigrade. But still, they saw no signs of the two liquids. For the experiment in Korea, they bring their samples of glassy ice, now cooled to -200 degrees. By quickly heating them up in the X-ray laser, they hope to catch a glimpse of the two liquids, right there in the fraction of a moment when the water molecules go from solid to moving. In a tiny ring with holes, they've prepared their ice samples, less than a millimeter thick. The sample ring is placed in the X-ray laser experimental chamber. With a powerful infrared laser pulse, they heat a tiny part of the glassy ice sample. And almost instantly, 10 nanoseconds after, they take a picture with the help of the brand new X-ray laser, exposing the result on a detector screen behind the sample. A flash much shorter than a trillionth of a second. The ring pattern on the detector screen shows the structure of the liquid. After the heating pulse, the liquid expands towards room pressure. Subsequent X-ray pulses will follow how the structure evolves. During the expansion, if there is only one curve present, it indicates only one liquid phase. If instead rings of small dots appear, it would reveal that ice has formed immediately without passing liquid water at all. And then, if instead 2 rings are generated next to each other, it would be evidence of 2 liquid phases. And the first shot, after 10 nanoseconds, shows just that. One bright, narrow curve, indicating 1 liquid phase of water. But now, things are starting to happen. The next shot towards the sample is fired at 100 nanoseconds after the heating beam. And here, a second ring starts to appear. And with the third shot, after 3,000 nanoseconds, The second ring is even brighter. At last, their endeavours pay off. The experiment is a success. They have pictures of the two liquids of water.
Imagine sitting in the control room and you have all these TV monitors in front of you. And we could actually in real time watch each individual X-ray laser shots on the sample. And then, boom, 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 the liquid transition was there, directly. Often when we conduct scientific experiments, we have to collect data, a lot of data, analyze it, run simulations, and after maybe many months or maybe sometimes even years, outcomes of graphs that we can interpret. But here, we saw it directly in real time. We actually conducted these experiments in Korea 3 different times, 6 months apart. And already the first time we had some hints. Second time we could see something, but it was really the third time where we could watch this liquid-liquid transition maybe 100 times. Because we have to repeat it and make sure that it always works. That's one of the standpoints in science.
And back in Stockholm, a scientific article is being written with the hope of getting it published in one of the major scientific journals.
We have now all the experimental data coming out for testing the liquid-liquid hypothesis, and we are just finished the analysis and the simulation that needs to be done, and we are just in the process to finalize the manuscript, and I think hopefully it will be submitted in a couple of weeks.
I think it's important to do this kind of articles because it helps us scientists to explain our research in a more simple way. And I'm learning now how to use social media to promote our science and make a little bit more the audience aware of what we are doing and attract more interest of the young people.
Getting an article published in a major scientific journal is definitely not a given. Within the science community, there is a lot of controversy. Every article is disputed and many are refused.
There was actually a previous article that was described as the war of super cool water. So that was a big debate in the community. People really fighting about that. Made it very interesting in the conferences to watch, actually.
Since proof of the two liquids of water is a huge discovery, but also controversial, the challenge for the research group is to scrutinize the experiment from every angle, to prepare for all possible counterattacks.
I think I take this one, Katrin.
They struggle with analyses, evaluations, and rewriting, and eventually it's sent. Now they just have to wait. And finally, a very pleasant surprise arrives in the Stockholm lab.
Okay, so I just posted this on Twitter. Our article came out today on Science. You can see the date here, 20th of November 2020. Very exciting stuff.
I bought the champagne this morning. I hope they took it down now. Hello everybody. So let's open the champagne. Cheers.
Every article that is published in Science undergoes a strict review process. And this is very good for the research because you have to do that. You have to get reviewed by your colleagues.
This paper is super important and very exciting because it's the first time that we have experimental evidence of this liquid and liquid transition in water.
In the beginning, people thought that this is impossible. Even people who predicted this from the theory, they said, oh, this is never gonna be able to measure that thing.
We know of no life without water. The hydrogen bonds that are really essential for the properties of water also exist in biomolecules like DNA and proteins. The big question is water only a solvent of life, or could the specific unique properties of water also play an important role in the life process? The ability of water to form two different liquids, could that also be important in the biological processes in the living cells?
Rather than looking at DNA as the instructor, as the organizer, as the master, we should look at DNA as a player together with the whole entire inner of the cell, the network. What role does water have in that? Could water be somehow involved in the information flow inside the cell? I think it's very likely.
We know of water as the liquid of life, but as science now has shown, maybe it has a more profound impact on the life process than previously understood. Maybe water works as a kind of computer network of nature, and maybe the two liquid structures of water could be the ones and the zeros. In Switzerland, Sylvie Roque's research group has performed a very controversial experiment that reveals that the insert of a single salt molecule in a volume of water immediately changes the positions of millions of water molecules far away.
The salt ions are changing the relative orientation of water molecules with respect to one another. If I have these two water molecules there, they're not randomly oriented. There is a correlation between the position of those water molecules. The longer distance these water molecules are, further away, the stronger our signal is. And that means that I have a single pair of ions and 5 million water molecules around that. So that's a very low concentration. Now, when we do the same experiments with polyelectrolytes that have charges on them, we have one polyelectrolyte molecule and 55 billion water molecules that are associated with that. So this is how low the concentration actually is.
That one single charged molecule immediately changes the correlation of 55 billion water molecules eternities away in relative terms is a groundbreaking discovery. It is the first evidence of water's ability to be affected at long distances.
Nobody really understands the dynamics of that liquid, within our cells, around our bodies. Just perhaps the insights we're getting at this fundamental level studying water will go full circle and feed back into the biological sciences that are such a big part of our research program and make truly revolutionary impacts into our understanding of the process of life and how it evolves. Sometimes science is amazing in its connectedness. Perhaps this is one of those times.
So if water enables certain structures of molecules, then you could, of course, extend this and think of the water as some kind of matrix that transports information from one molecule to the other.
A low density pops up somewhere in the liquid, high density pops up somewhere in the liquid. And if we have a biomolecule, a protein, a DNA, a membrane in the cell, these fluctuations might no longer be random. And if these fluctuations are extended over a very long length scale, just like Sylvie have demonstrated, it could be possible that that actually is the mediator. Water is the mediator in this communication.
So when things happen in the left end of the cell, the right end of the cells knows about it, feels that something has happened at the other end of the cell within time sequences which are nanoseconds, picoseconds, are the most short, possibly short time sequences. And what role does water have in that?
And future experiments has to test this hypothesis. All my life, I've been so fascinated by water. During the summers, when I was a boy, I would spend almost all hours swimming and playing in the lakes and ocean. When I became a scientist, I assumed that everything was well understood about water, being made of such a simple molecule as H2O. I've come to understand that it's not that simple. It is so remarkable in every aspect. Could it be the question about the structure, dynamics, rearrangement in the liquid form of the water molecules, and its connection to the life processes is one of the major scientific questions of our time.